single angstroms, you have to have a pretty good microscope to see them. This is something called F-actin. It's like a strand of a protein, and you can definitely see the segmented nature of it. So that's a pretty image of 0.8 by 800 by 800 nanometers. So it's a pretty good sized molecule. For me, if you say something's big, you know, that to mean micron's big, you know. So when you're a nanoscientist, everything beyond a couple hundred nanometers is just big. These are tapping mode AFM images of actin filaments. Again, another protein that organizes together into these interesting strands. We can actually see them and study the changes in them when we do chemistry with them. These are collagen. Collagen's another important protein. And zooming in to see the sides of the collagen, you can see the ribs and the actual detailed structure, the very intimate details of what your molecules look like. And that's what AFM can do. And imagine your children and grandchildren will be seeing these in their own schools probably in the next couple of decade or so, maybe 10 years, maybe 10, maybe 15. This is collagen again. This is a different view of collagen. As you zoom in or zoom out, they look bigger or smaller. But again, you can see the segmented nature of it. And this is another view of collagen fibers on a substrate, where you can see the regular periodic bands that are all spaced the same distance apart. All right, these are cells, endothelial cells. Cells are big. Cells are usually on the order of at least, tens to hundreds of microns. So sometimes you're looking at cells, you're looking at 10 microns or so. But AFMs can be designed to look at micron-sized things pretty well too. You can see fine structural details you cannot see with an optical microscope. Remember, optical microscope things have to be transparent. AFM, you're just imaging, you're using your probe. You're scanning your probe over the surface and it tells you what the shape of that object is. And these are bacteria. Of course, bacteria are something that you can measure and look at with an AFM. Bacteria are round or flat or square. We can look at the different types of bacteria in a way we never could see before with the intimate details of how does the surface change when you have an antibiotic bind to it. That's what we care about, killing those bacteria most of the time. This is bacteria, more bacteria, views of bacteria and the flagella of the bacteria. You see these spirals along here? They're what wiggle and propel the bacteria around in solutions. You can do a zoom in close-up look at those flagella. You can't see those with a regular optical microscope. They're much too small. And here's some more biofilms. Pseudomonas putida. If you were Latin, you'd probably pronounce that correctly. But you can look and see the very fine detail of what the surface of a bacteria looks like. And this is very interesting to biologists with AFM. This is a study that was done by my advisor in Detroit at Wayne State University, where they looked at metal treatments of the surface and looked at how the surface changed. So these are the healthy bacteria on the top row, and these are the treated bacteria where you can see that something called the LPS layer, the surface layer of lipopolysaccharides, were removed by the treatments of the drug that they were studying, how these drugs affect bacteria. And so you look at the big view, you see the shape of the rods. These are the bacteria. These are the bugs, and this is the surface of one, like the square area. You zoom in on that square area, you can see the fine details of those structures. It's a whole new way to study bacteria. These are polysaccharides. This is like another biomolecule, and you can see the strands and filaments and see how they are arranged on the surface. You can measure their sizes and dimensions and see if they bind to other molecules and where those molecules bind. This is a tangled network again of something called polysaccharide xanthan. And these are purple membrane filaments. These are from the bacteria rhodopsin, another important biological protein that's being studied that has to do with the optics, with light conversion in optics. Red blood cells, everybody has those. If you took your blood and you put it on a glass slide and you put it under an AFM, that's what they would look like. You see the individual blood cells you can see with an AFM. And there's another view of a red blood cell. With an optical view here, this is what you see with the optical view. And with an AFM, you can really see the details of the shape of the red and white blood cells with your AFM. So of course, AFM can look at atoms, it can look at molecules. This is collagen toxin oligomers bound to a lipid bilayer, whatever that is. You can look at all kinds of biological systems. And if they have a interesting shape or morphology, the tip, if you have a very sharp probe, this person does really beautiful work. He's in Switzerland, I believe, is that you can just reveal amazing details that we never could see before using an atomic force microscope. Okay, part 4, molecular fabrication by AFM. This is what my lab is known for. This is kind of hard to explain, but okay, so we don't have wrenches and tools to put molecules together with our hands. So we do it in solution. And we design the molecules so that they bind to each other. And so we can make really small things in my lab. I'm going to spare you the details. Well, maybe not. I'll tell you a little bit about the details. We use an AFM tip for some of it. We use an AFM tip to like scrape away areas of the surface, or to as like we can coat the tip with molecules and deposit them on the surface in certain arrangements. We can put a catalyst and have selective surface reactions only where the tip touches the surface. Or we can use force and have new molecules in solution, scrape one area away, put new molecules down. These are some of the techniques we use. So that was just enough detail right there. Okay, these are some structures we made. So this is a 100 nanometer ring. The ring itself is only 100 nanometers from one side to the other. The actual width of the ring is like 20 nanometers. We're pretty small here. This is what my students can do. The undergraduates do this in my laboratory. They can make rings that are taller or shorter, depending on how tall or thick the molecules are. So we're writing patterns with atomic force microscopy. Of course, if we can make circles, we can make squares. We can make the squares, if they're bright, they're tall. If they're dark, they're shallow. So these are what pictures of arrays of squares, and it takes us about 3 minutes. 3 minutes to draw 15 to 20, 25 patterns. These rings only took less than a minute to draw because we were just drawing a circle. About as fast as you could trace it with your finger, the AFM can write, because you're using a tip to write these patterns. And of course, then we do chemistry. We do chemical reactions, very local, tiny, and we build things from the bottom up. We assemble the next molecules according to the chemical reaction that we designed to link one kind of molecule with another molecule, and we make squares of different and circles of different kinds of molecules. Okay, the undergraduates did this in their laboratory. They make stick people, you know. It just takes a little, I need some more creative students in my lab, you know, that can decide. We made